So before I start the proceedings of this feedback amplifier, let me just tell you what is feedback all about. Hopefully you know what is feedback. In fact, the term feedback is involved everywhere, every system that we deal with in practice. For example, our biological system, it involves some feedback. For example, there is a say for example, right, that part, or suppose there is a viral infection, a bacterial infection, right? So some abnormality will be there, and based on that, you give medications, so that once again it becomes stable, right? The biological system involves some feedback. Whenever a person, suppose, is suffering from say high blood pressure or low blood pressure, if it exceeds a certain limit or if it goes below a certain limit, then normally you see that person, what is the symbol, what is the symptom that when a person is having excessively high, excessively low blood pressure.
Basically, output time change
faint, yeah. That's a symbol. Falling, right? That's a symbol. And accordingly, this biological system takes care of that particular person, the blood pressure. Now come to any organization. Everywhere you find the feedback. Everywhere. For the smooth running of any organization. If you visit any shopping mall or anywhere, you'll see that there is a feedback. Very close to the cash counter, there is a feedback. For the betterment of that particular organization. Right? In finance also, you have feedback. Right? Any example? That finance involves some feedback? Finance. So that everything becomes very stable. Whenever there is no such feedback, it is expected that something is going beyond the limit. Something unexpected. When everything is stable, a financial system, if I say that okay, it's a stable one, right? That means it has to involve something. For example, if you observe the pattern of, if you observe the pattern of in the share market, right? The way this senses goes up and down, that particular thing, it involves feedback, depending upon the rate. And mostly, if you consider a political system, it involves feedback. Right? Every 5 years, there is an election. So what is the need of feedback? The need is that to make the system stable, so that the performance remains at its level best. Now, coming back to our discussion, hopefully you have studied what is amplifier, electronic amplifier in fact, using bipolar junction transistor. You can also use other device. For example, you can also use a MOS device, MOSFET, as the building block of amplifier. But in this particular course, we have used the bipolar junction transistor BJT as the basic building block of an amplifier. We have discussed several types of amplifier, like common emitter amplifier, common base amplifier, common collector amplifier, and the cascade amplifier, common emitter, common base cascade, which is also known as cascade amplifier. So all of them can be grouped into the single-ended amplifier. And lastly, we have discussed about what is meant by a differential amplifier. Now, while studying this, say single-ended amplifier, the common emitter, common base, common collector, knowingly or unknowingly, you have also studied the feedback. The feedback was also there, but you did not understand that feedback was essentially there. Now today, we will introduce formally, for the first time, we will introduce what is feedback. So for any system, if I call a feedback system, it involves a feed network or feed forward network, something like that, and a back network, something like this. Typically, whenever we represent any system, the notion is that we expect that the input is applied from the left side and the output is applied from the right side. That is a typical description, isn't it? Typically, what we do? Typically, we do something like this. Suppose this is my system, any system is. Typically, we represent the input from this side and output from the right hand side. That is the signal flow from left to right. Okay. So the same thing is also followed for this feed network or feed forward network. The input is SI, I stands for input, and output is SO, O stands for output. When it comes to the back network, intentionally I have written the back in that way, so that the input for the back network is obtained from this side. Right? So input for the back network is obtained from this side, and output is obtained from this side. So if I observe the feed network from this side, then you have to observe the back network from that side. Okay? Which one? No. You have to observe from this side. You have to place the mirror accordingly. Suppose the mirror is placed across this board. Right? So here you are observing the system facing towards the board. Right? So that the input is applied from the left hand side, output is obtained from the right hand side. And whenever you observe this back network, then you are facing this particular network, back network, from the other side. Right? So once again, for the back network, if you observe the back network from this side, then the input is obtained from the left hand side and the output is obtained from the right hand side. But since you are observing this feed and back network together, so that's why there is a change. So it seems that for the back network, the input is obtained from the right hand side and the output is obtained from the left hand side. But remember, the operation is just the opposite for the feed network as well as for the back network. Now, what is the purpose of this back network? It basically controls everything. The output of this feed network is provided as the input of the back network, and it performs something. It processes that output. That output SO is obtained over there, and it is processed by this back network. And a portion of this output is once again fed back. Right? And then some mixing takes place over here. And then this mixed output is fed to the feed network. So basically the operation of the feedback network consists of two different things. One is known as the sampling part, and second one is known as the mixing part. The way the feedbacks are collected, for example, in our system, in our education system, we have so many feedbacks. As you know, our department is accredited with NBA. So therefore, we have so many feedbacks. We require so many feedbacks from our stakeholders. We require feedbacks from the students. We require feedbacks from the alumnus. We require feedback from the employers. We require feedback from the parents, guardians. We require feedback from the industry personnel. They are the stakeholders. So how to collect? Maybe anonymous feedback may not be. How to collect? You can collect the feedback using pen and paper, simple, hard copy, or using Google form, or any other form, soft copy. So the way the feedbacks are collected, this is nothing but the stamping, right? You are gathering the information, you are gathering the response from the stakeholders for this university, for example. And then this is obtained over here, and then what you are doing? Now, the university organization, the university administration, now what they are doing, they are now analyzing that feedback. Some good things, some bad things. This is coming. Something very encouraging, something is not like that encouraging, and we will analyze all these things. This is performed inside this back network. And based on that, the input that we are providing, for example, for the creation of your curriculum, for the formation of your curriculum, typically we have to have so many brainstorming sessions with the stakeholders. In which case we have the departmental faculty members, we have the alumnus, we have the industry personnel, all of them put their comments. in framing the syllabus, the UG course or PG course or PhD course, whatever it may be, the coursework for PhD as well. So it involves two things. So any feedback network, any feedback system involves two things. One is the sampling part, the way you collect the data, you gather the data, and the processing part is there obviously, which is performed in the back network. And after this processing is over, then how are you feeding this back? And this process is known as a mixing part, mixing operation. So for any feedback network, you have two operations. One is known as the sampling operation. Second one is known as the mixing operation, sampling and mixing. And typically we don't say mixing and sampling because first the sampling has to be done. First of all, you have to collect the data, no? You have to collect the information. Here in our case, you have to collect the signal. And then you have to feed it back. You have to find, after you process the signal in the back network, then you have to feed that particular part at the input of the feed network using this mixing operations, mixing circuit. Now, based upon the mixing that you perform, you can have a positive feedback, you can have a negative feedback. For example, if this input SI is represented by SS is your actual input. SS was your actual input. For example, suppose, let me frame from that. We are going to frame a curriculum for the UG students of this department. You have to frame a curriculum. So initially, if there is no feedback, so what is to be the procedure, standard procedure? If there is no feedback, that means there is no feedback. This back network is absent. This is absent. That means the students who have passed from this department, say in the year 2000, they have studied a number of papers, and if there is no such feedback involved in the system, then you are also supposed to study the same set of papers, which might be obsolete, which might be redundant, is not needed. So typically what we do, after every 4 or 5 years, there is a meeting, a lot of meetings, held with the stakeholders, the faculty members, the alumnus, and the industry personnel, and then obviously the experts in the academic field, and then a brainstorming session. And after that, we decide, okay, these papers, there are a few papers which might not be relevant to your case. There are a few papers which are well known to you from your school days, for example. We can scrap those papers, and we can also include new papers, state-of-the-art papers, courses, right? So some positive, some negative, some inclusion, some deletion. So deletion has to be there. If there is no deletion, then you just imagine what will be your scenario. 40 papers, 20 years back. After 20 years, 45 papers in 4 years. After another 5 to 10 years, say 55 papers. So if there is no deletion, that means the coverage you are supposed to have in this 4-year course is going to be tremendous. So if your system involves in the mixing process, if it is only positive, plus, no minus, try to imagine what will be the scenario. Right. So typically mixing involves, now if there is a negative sign over there, SS minus SS, negative feedback, that means so if I have a positive feedback, then you have to maintain certain criteria. You have to maintain certain criteria, and we will discuss this thing in the next unit whenever we discuss the oscillator circuit. So forget about that for the time being. So typically, if the back network involves this SS minus SF, that means the way the signal is mixed. The original signal was SS, and the back network processes this output SO in the form of SF, and if this SS and SF, they are added in the opposite phase, not in the same phase, SS minus SF. That means if SS increases, then SF will drop, something like that. Then this kind of feedback is known as the negative feedback. However, if they are added, if they are in the same phase, in that case what happens? If they are in the same phase, then ultimately there is a problem of stability. Right? So SI, this input signal, is equal to SS plus SF, the summation of these two, then we call it as a positive feedback. And if the input signal SI is given by SS minus SF, then we call it as a negative feedback. In this particular unit, we will study the negative feedback in particular. Okay? Any doubt up to this? Any doubt? Okay, so let me move. Okay. Before I move, let's find out some relation between the different parameters present over here. Now this feed network is having a system function equal to A, and the back network is having a system function equal to B. So what is meant by that? This output of the feed network is equal to S0 or SO, and the input is given by SI. So what is the relation between SO and SI? SO is equal to A times SI. Similarly, for the back network, the input is given by SO and the output is given by SF, right? So the back network, what I can write, SF is equal to B times SO. Okay, and how this SI, SF and SS they are related for a negative feedback? SI is equal to SS minus SF, right? So SI is equal to SS minus SF, and this SF is nothing but B times SO. And what is SO? A times SI. So I can write SI as SS minus AB times SI. So if you simplify this one, then what you are getting is SI into 1 plus AB is equal to SS. And for the feedback network, if you just observe the feedback network, which has been identified by means of this red box, red dotted box, the input to the feedback network is equal to SS, and the output of this network is equal to SO. For the feed network only, the input is SI, output is SO for the feed network. But whenever it involves a back network also, this entire combination is feed and back together, then the input is given by SS and output is given by SO. So therefore, for the feedback network, the gain of the network is represented by SO upon SS. So if you just substitute this value, then what you are getting, SI you have already got, SI is equal to SS upon 1 plus AB, and SO is equal to A times SI. So therefore, the gain with feedback is represented by A upon 1 plus AB. A by 1 plus AB. So without back network, if back network was absent, had there been no back network, that means B is equal to 0. In that case, what was your gain? The gain was A, simple A. That means there is no back network. That back connection that was completely absent. That feedback was not there. If you have feedback, then the gain with feedback is given by A upon 1 plus AB. A upon 1 plus AB. So what is the implication? The implication is that, remember that this 1 plus AB is greater than 1, right? AB is greater than 0. There is a product A into B is greater than 0. So 1 plus AB should be greater than 1. So therefore, the gain with feedback will be less than gain without feedback. So if you incorporate feedback, that means there is a reduction in gain. But at the cost of what? So gain is reduced, but at the cost of what? At the cost of stability. So we will see to it. For example, suppose you have a system like this, a simple system which involves no feedback element. You have the system is represented by this A, input is given by SS, output is represented by SO. So SO is equal to A times SS. Suppose the particular gain of this system increases by X%. X can be anything, 10%, 20%, 30%, can be anything. Now if there is a change in the value of A, then SO will also change by the same percent. Isn't it? Because SO is equal to A times SS. For the same SS, if A increases by X%, then SO will also increase by X%. For example, suppose initially the gain is equal to 100. So what is your SO? SO is equal to 100 times SS. Then suppose the gain increases by 50%. So the new gain becomes 50. 100 plus 50. So what is your SO? That is 150 SS. So previously your SO was 100 SS. This time the gain is, the output is 150 SS. So if there is a change of 50% in the gain, that means the output also changes by the same 50%. Because there is no back network, you don't have any control. You don't have any control. No back network is present. Okay. Now come to this side. Now here what you have explicit back network present over here. You have this feed network apart from this explicit back network. Then your S naught is given by A by 1 plus AB times SS. And suppose let's assume that A is equal to 100, the same A, and let's take B is equal to 0.1. Because the fraction of the output voltage or output signal will be mixed at the input side. So with this particular combination, A is equal to 100 and B is equal to 0.1, what is your SO? If you simply calculate 100 by, it is like 100 by 11. 100 by 11. That is coming out to be 9.1. SO is equal to 9.1 SS. A by 1 plus AB. That is the formula. A by 1 plus AB. If you just substitute those values, A is equal to 100 and B is equal to 0.1, then SO is coming out to be 9.1 SS. Relatively small. With respect to 100, it is 9.1, relatively small. But what is the advantage? Now suppose the gain increases, once again the gain increases by the same 50%. So from 100, it becomes 150. Right? So now what is the new SS? New SO? This new SO is 9.375 SS. If you check the percentage change, this is only 3%. 9.5, 9.1 previously, this time 9.375. If you don't have any feedback, 100 SS to 150 SS. So 50% change, 50% increase in the gain results in 50% change or 50% increase in the output voltage, even if the input is same. Right? Whereas in this particular case, when you have incorporated some back network inside the particular system, then although the gain was less, it's 9.1 SS, and this time it is 9.375 SS. So 9.375, 9.1, so only 0.275 by 9.1. If you just calculate, it is coming close to 3% change only in output. So if you have changed the open loop gain by 50%, this A is called open loop gain. That means there is no connection. That's why it is called open loop. There is no connection. So 50% change in open loop gain results in only 3% change in output for fixed input and feedback. That is advantageous. B is known as a feedback method. B. In the back network, you have some fraction, no? That B. This B is known as a feedback factor. Because not the entire output will be mixed, a portion of the output will be mixed. It's not that the entire output. This back network, this particular back network, accepts this output as its input, S naught or SO, and a portion of this output is processed and it is fed back at the input of the feed network.
That fraction is big.
Yes, so if it is 0.1, that means only 10% of the output will be fed back, will be mixed. Okay.
Output is stable enough.
So that the output remains stable. Okay. So that we can also prove. So in this particular slide, what we have used some numerical values for A and B, and accordingly we have verified this one. You can also do the same thing mathematically using that particular formula. So already you know that gain, closed loop gain without feedback, it was A. Closed loop gain with feedback or gain with feedback is given by A by 1 plus AB. We have already verified that if there is no such B, if there is no such feedback network, then the overall system is not at all stable. Now you may argue, how can the system be unstable? You have already seen there are so many examples, there are so many instances because of which the gain of any amplifier might become unstable. For example, if there is a temperature fluctuation. Different environment, temperature fluctuation, beta will rise. If there is a temperature fluctuation, some ICO will increase. The reverse, if you just consider that particular current, leakage current, right? If the temperature changes, this VBE that will drop, right? So because of this, now if in your ultimate expression, if you have some beta dependent parameter, if you have some temperature dependent parameter in the expression of the voltage gain, then obviously you expect that this particular system or this particular circuit is not at all stable. Suppose you have designed some amplifier at room temperature at 27 degrees centigrade. Suppose the gain is found out to be say 50 voltage gain. Now you perform the same experiment. You perform the same experiment at 45 degrees centigrade. Then you verify that the gain is becoming 60. That means 20% change. Now if there is a 20% change in the gain expression, and if there is no such feedback, then it results in 20% change in the or 20% increase in the output voltage as well. Right. So in your system, you must be having some mechanism inbuilt. Inherent mechanism should be there so that these external perturbations can be arrested to some extent. That means even if some external perturbations is there, even if some temperature changes or temperature reduces or beta variation is there, still your system, your circuit is capable to get rid of that particular change, to arrest that particular change by virtue of a feedback connection inside that amplifier circuit. Okay, so that we have already explained using some numerical values, and you can also explain this one using mathematically. You can verify this one, this DAF by DA and DAF by AF upon DA by A. That means the percentage change. What is DAF by AF? That means the corresponding change of in the feedback. The corresponding change in the closed loop gain. And here, this is the percentage change of the open loop gain. This is the percentage change in the closed loop gain. This is the percentage change in the open loop gain. DAF by AF upon DA by A. You should expect that thing, that means this value should be large with respect to this value, or this fraction should be less than 1. That is expected. That means the open loop gain, the change in the open loop gain, last time we have seen that the change in the open loop gain was 50%. And the change in the closed loop gain is only 3%. Right. So therefore, mathematically you can also prove this is coming out to be 1 by 1 plus AB, which is always less than 1 because 1 plus AB is greater than 1. And this 1 plus what is the role of this 1 plus AB? This particular factor, you have also noticed this 1 plus AB in the expression of the closed loop gain. What was the closed loop gain expression? It was given by A by 1 plus AB. So this 1 plus AB term was there in the closed loop gain. So closed loop gain is equal to open loop gain divided by the 1 plus AB, that particular factor. And if you just compute this percentage change, if you compute the ratio of the percentage change of the closed loop gain to the open loop gain, this is also coming out to 1 plus AB. 1 by 1 plus AB. So this 1 plus AB, this term is known as the desensitivity factor. 1 plus AB is known to be the desensitivity factor because it desensitizes the gain or the variation. It desensitizes the variation in the output voltage. Okay, that is one of the advantages of this feedback network.
Closed loop
gain is given by A by 1 plus AB. If you don't have any feedback network, any back network, then this is your the gain, that is A, which is known as open loop gain. Open loop gain. And closed loop gain means what? When you have a proper loop present over there. Then for this, what is the gain? A by 1 plus. For this, the gain is only A. And for this, the gain is given by A by 1 plus AB. The advantage is that the gain is becoming much more desensitized with respect to external fluctuation. Desensitized, that means it's not that sensitive. Previously, if there is a change in A by 50% or say 10%, the corresponding change in the output is also by the same percent, 10% or 50%, because there is no such restriction. S0 was given by A times SS. So if A increases by 50%, then also your S0 will increase by 50%. But this time, if you just observe this expression, you have A in the numerator as well as A in the denominator. Right? Can you remember one such expression that you have got, like GM in the numerator, GM in the denominator? We'll discuss in detail. That time I told you, no, Gm is there in the denominator as well as Gm is there in the denominator. In one case, you have the Gm in the numerator only, Gm minus Gm right? In other case, you have seen that Gm is there. Gm is there in the numerator as well as Gm is there in the denominator. That means, if there is some change in the Gm value, that means it will affect both the numerator and the denominator, right? So the overall change will be restricted to some extent. Okay, so that is one advantage to desensitize the gain, and second one is known as a bandwidth extension. Bandwidth extension. We have not discussed bandwidth yet. Still, I can tell you very briefly. Typically, what we expect. Typically, in our last unit, we have discussed or we have assumed that the gain is fairly constant. Gain is fairly constant. That means all the effects of the frequency sensitive elements, like the capacitors, inductors, we have just got rid of those. We have assumed that the capacitor is acting as a short circuit whenever it is there in the series path, and it is acting as an open circuit whenever it is there in the parallel path. But typically, you don't expect that the gain is fairly constant. It is constant over a mid-frequency range. If the frequency is very large, then the gain will drop. If the frequency is very small, then the gain will also drop. So typically, we can represent the gain with the expression for the gain by virtue of this expression. AS is given by A naught upon 1 plus S by omega H. What is that? That means what is S? S is the frequency term. So as S increases, frequency increases, then obviously this term will also increase, the denominator, and accordingly this entire fraction will reduce. So typically what happens for very large frequency, the gain drops. We will discuss this in detail whenever we will talk about the frequency response of the amplifier. Right? And here this omega H is known as the higher cutoff frequency. Higher cutoff frequency. Because if S is equal to omega H, then you see that this AS drops now. This is 1 by root 2. 1 by root 2. If this is equal to, say, suppose A naught is equal to 10, and if S is equal to omega H, then it comes out to be 10 by root 2. No, you have to find out, because remember this S is a complex number. It's not 2. S is a complex number. S is represented by J times omega. Okay. Yes. So this one. Yes, this AS is equal to A naught. A naught is the midband gain divided by 1 plus S by omega H. Right? So I can represent this S as J omega. A naught 1 plus J omega by omega H. So this is a complex term. So we have the phase as well as the magnitude. So what is the magnitude? So mod of A J omega, if I call, this is nothing but A naught upon square root of 1 plus omega by omega H whole square. Right, so when omega is equal to omega H, this is equal to A naught by 1 by A naught by root. This is also called a 3 dB point.
Equation to LOT.
For the time being, let's assume that AS looks something like this. Right? Next, in the next class or in the next unit, whenever we move to the frequency response of the amplifier, they will understand that this AS, because it is not that simple. You can have more number of poles. It's not that only one. Okay. Anyway, so what I understand, the bandwidth of the amplifier without feedback is given by omega H. So bandwidth is that particular frequency or higher cutoff frequency where the gain drops to 70.7% of the maximum gain. That is the scenario without feedback. Now with feedback, what happens? Now with feedback, I can write this AFS is equal to AS by 1 plus ASB. It's not simply AS by 1 plus ASB. Now if you just simply plug in those values, AS is equal to A naught upon 1 plus S by omega H, and if you just substitute those values, then ultimately what you are getting in this particular form, AFS is equal to A naught by 1 plus A naught B multiplied with 1 by 1 plus S by omega H into 1 plus A naught B. So this entire thing, what is that? A naught by 1 plus A naught B. This is nothing but AF, gain with feedback. So therefore I can write this as, and I can write this entire thing as omega H F. Right. So this AFS is nothing but AF by 1 plus S by omega HF. Looks similar. If you compare this one with this one, looks similar. A naught by 1 plus S by omega H. Here you have AF by 1 plus S by omega HF. AF is less as compared to A naught. Right? AF is equal to A naught by 1 plus AB. What about this omega HF? This is enhanced. Omega HF is enhanced. Omega HF is equal to omega H multiplied with 1 plus A naught. Right? So sustainability. Once again, a note of last bench. Note of. I have told you the last bench sustainability, or rather kind of like the robustness of the design. Robustness of the design. The sustainability. So gain might be small. Gain might be small. So whenever you incorporate feedback, what happens? The gain might be small, gain is less, but it sustains for a wider range of time. I have given the example of Amitabh Bachchan last day. Lata Mangeshkar last day. Right. So the duration over which they are performed is prevailing. That duration is very important. Region, yeah. That region. So here, in case of amplification, that region stands for the frequency range, over which, if I incorporate the feedback, then the gain drops to some extent. Right? But the range over which this gain is sustained, that is important. Nowadays, you know that in every session, whenever these IPL matches are being played, in every session you will see that that particular star in one session. Suppose in 2021 you have some star, in 2022 you have some other star, 2023 some new star, something like that. Every new IPL season, then new star is coming. That means their behavior, their performance is good only for that particular session only.
Sustainable.
But they are not sustainable. Now if I give you the example of Virat Kohli, so his performance for the last 10 years, last 15 years, you just observe. It might be that for the last 10 matches, last 5 matches, the performance is not that good. That might happen, that might happen. But if you just observe the behavior, observe the performance, observe the run over a range of say 10 years, 15 years, much better. So if I have some, say for example, say after say 30 years, after say 40 years, now if something is written on Virat Kohli or something is written on some other star resulting from this IPL, then according to you, who is going to win the match? Obviously. Because the sustainability, the span. That means the stability. Right? So you have this notion of feedback everywhere. Right? Okay. Is that basic understanding clear to you?
Yes, sir.
Clear? Basic understanding? As of now, we have not told anything about the circuit and all. We have just explained what is feedback and how it helps in stabilizing the entire thing. And then gradually we will move into the circuit part of it. The feed network, the back network. As of now, we have used simple black boxes to represent those feed network and back network. Simple black box. I don't know what is there inside. Now I can have some circuitry inside. Okay. Now before that, as I've told you, the feedback involves two operations. What are those?
Feed and
Receive.
oh,
What are those two operations?
mixing and sampling.
No, not feed
Mixing
and
and
back.
sampling.
One is sampling, second one is mixing. There are two operations. Feed and back, these are the two blocks. Right. The operations the operations are sampling first and then mixing. Right. So when it comes to electronic amplifier, then which parameter can you sample?
Frequency.
Not frequency.
Signal.
Yes, signal. You can sample the signal. But what kind of signal? For our case,
Sinusoidal.
not sinusoidal. What kind of signal?
Voltage.
Voltage might be a signal
Sorry.
or might be a current. That you can measure, no? Either voltage or current. Whenever you sample something, either can be voltage or it can be current. Right? You can sample either voltage or current. Now, how can you sample the voltage? You tell me. How can you sample the voltage? Yes, but how to connect? How to connect? Using a voltmeter, you can measure the voltage. But how to place this voltmeter into the circuit? Parallel or shunt connection, right? Okay. And for current series. So if you have to sample the voltage, so you can sample either voltage or current. Similarly, you can mix what? You can mix either voltage or current. Because these are the two variables at our disposal. One is current, second one is voltage. So you can sample the voltage, you can mix the voltage, you can sample the current, you can mix the current. Right? You can sample the voltage, you can sample the current, you can mix the voltage, you can mix the current. Now, how to sample the voltage? In order to sample the voltage, you have to place something in parallel. How to sample the current? In series. Right? And for mixing, this is completely opposite. Why? Because suppose I am having a 5-volt battery. Okay? Suppose I would like to make it a 4-volt. Right? So 5-volt minus 1 volt. That means you have to connect in series. You have to apply KVL. Okay. So whenever you are mixing the voltage, mixing is done in which path? Mixing is done in series path for voltage. Similarly for current, suppose we have two branch, say A and B. Suppose 1 milliampere is flowing. I would like to make it 0.9 milliampere or 1.1 milliampere. So you require another current source in parallel, right? Between those two nodes.
0.89.
So that is very much confusing. It's not that voltage is always equivalent to voltage is not always equivalent to parallel or shunt, and current is not always equivalent to series. When you sample the voltage, then this sampling has to be done in parallel. When you sample the current, this sampling has to be done in series. When you mix the voltage, then this mixing has to be done in series. When you mix the current, then it has to be done in parallel. In order to sample the voltage, suppose let me move to the next slide. Yeah. Suppose this is one node, say VA, this is another node, say VB. I'd like to measure the voltage between these two nodes. Or I should not make it short circuit, otherwise it can create some confusion. Suppose I don't know what is there. There is a black box. These are the two nodes A and B. I would like to measure what is the voltage between these two nodes. I don't know what is there inside. Right? How to measure? Using a voltmeter. How to place it in parallel. Right? To sample it, I have to place it in parallel. Okay? Suppose I would like to measure what is the current that is going through this AB. So I have to connect this ammeter in series. Okay? The sampling part is okay? Okay. Next comes the mixing part. So for mixing, suppose I am having a 5-volt battery like this between these two nodes, plus minus 5 volt. I would like to make it 4 volt. How can I make it 4 volt? So I have to connect another like this, minus plus 1 volt. So that it becomes 4 volt. Right? So I have to connect in series for mixing. Similarly, suppose I am having, say for example, between these two, suppose I am having 1 milliampere current between, say, node B and node D. Say for example, I would like to make it, say, 1.1 milliampere. How can I do that? So 1.1. So 0.1 like this. If it is 0.9, then the direction will be just the reverse. Right? Any doubt? Anybody having any doubt? So for current mixing, this is to be done in parallel path. But current sampling, series. Voltage mixing, series path. Voltage sampling, parallel path. If that part is okay, then you understand most of it. Okay. So basically we have 4 different combinations. This side is sampling. This side is sampling. This is a matrix. 2 by 2 matrix. This side is sampling. This side is mixing. So sampling can be voltage sampling or can be current sampling. Right? So when the sampling is, whenever you are sampling a voltage, you have to connect thing in shunt. Whenever you are sampling a current, you have to connect thing in series. Okay? Then whenever you are mixing something, you can also mix the current, you can also mix the voltage. When you mix the current, that mixing has to be done in shunt path, and when you mix the voltage, this is mixed in the series path. Okay? Now traditionally what I say, or what I personally prefer, in many books you will see that voltage sampling, voltage current sampling, current voltage sampling, current sampling, right? Or series sampling, series current, series sampling, series shunt sampling, shunt series sampling, shunt sampling. Shunt feedback rather. Typically, what I prefer is for the sampling, I refer the variable that I am sampling, and for mixing, I prefer the mode. Right. So if it is like, if I call it like voltage shunt, that means voltage sampling, shunt mixing. There are so many terminologies. You can also call it like shunt, current shunt. You can also call it current shunt if it follows mixing sampling nature. Typically, people say that first sampling, then mixing. First sampling, then mixing. So voltage shunt. That means you are sampling voltage, you are mixing in shunt. Similarly, current shunt. You are sampling the current and you are mixing in shunt path. Voltage series. You are sampling the voltage, you are mixing it in series. And finally, the current sampling and series mixing. Okay. Current sampling, series mixing is your current series. So you have 4 different terminologies: voltage series, current shunt, current series, voltage shunt. Now suppose every time it is sampling mixing format, right? Not the other way around. Not like mixing sampling. It is always sampling followed by mixing. Because first sampling, then mixing. If I call your feedback is like voltage. What does it mean? Voltage.
voltage sampling, voltage mixing.
Voltage. So voltage means what?
Voltage shunting, voltage series.
No. Voltage means what?
Voltage sampling হচ্ছে voltage mixing.
Means out of these 4, which one is correct?
Voltage series.
Voltage series. Right? We call it voltage current. That means voltage
Shunt.
series. Voltage current. That means voltage shunt. Current.
Current shunt.
Current shunt and current voltage.
Current series.
Right? So we have four such terminologies: voltage shunt, voltage series, current shunt, current series. Sometimes some other books you can also see like voltage mixing, current mixing. I mean current feedback, voltage feedback, voltage current feedback, current voltage feedback. Don't get confused. Voltage means voltage, and next the first voltage is the sampling part, and the second voltage is the mixing part. So when voltage mixing, that means the series mixing. So voltage means voltage series. You can also check from here, voltage. That's why I've written in brackets. Voltage. That means voltage series. Voltage, current, that means voltage shunt. Current, that is current shunt, and current voltage, that is current series. Clear? All right. Okay. Now let's move to the circuit first. Also, this is represented in the block diagram format. This is the feed network. This is the back network. Okay. Output voltage. So each of these black box is represented by a two-port network. Hopefully, you understand what is meant by two-port network. The two input port. You have this input port over there. You have output port over there, right? So for this particular network, this is output voltage, and the way this is connected, the way the output signal is connected to the input of the back network. How is it connected? How do we check the output signal, or how do we measure this? How do we sample this output signal? I'm mentioning like output signal, not voltage or current. Now, whatever we're doing, are we sampling voltage or are we sampling current? We're sampling voltage. Why? Because voltage sampling is written over there. Why? Why voltage sampling? Because it is written over there, voltage sampling. Why voltage sampling? Why voltage sampling? Because this is the input of the back network. This is the input of the back network. Now, how is it connected to the output of the feed network? In parallel. So we are sampling the voltage, right? Then how are we mixing? There was a loop. That port was the input port was there, and this input port is broken, and then this is connected like this. Actually, previously what was there? It was something like this. That was the back network. The input of the feed network. Then this loop is broken and accordingly connected. So that's why it is known as the series mixing. Series mixing. Series mixing. You are mixing in series. That means you are mixing voltage. Right. So voltage series, or you can also call it voltage kind of thing. Okay. So for the feed network, what is the input? Input is the voltage. What is the output? Output is also the voltage. So this feed network is nothing but a voltage amplifier. Feed network is a voltage amplifier. Because input is also voltage, output is also voltage. Right? Now, if you are interested in finding out the voltage gain with feedback, what is that? AV by 1 plus AVP. So how P is related there? What is the formula for B here? How can we represent B? VF by VO. That is B. Right? And suppose initially this particular feed network, without the connection of this back network, it is having an input resistance equal to Ri. Now you understand what is meant by input resistance? You understand what is meant by input resistance? So initially that input resistance is Ri. Now, whenever you connect this back network in series like this, suppose the new input resistance of this feedback network becomes RIF, input resistance with feedback. Now the question is that, what is the relation between this Ri and RIF?
Sir, can you repeat once? RIF.
Ri is basically the input resistance of this feed network. Right. Now we are interested in finding out, so what is that? This is basically the input voltage upon input current. Now we are interested in finding out the input resistance of this overall circuit. Right. So for the overall circuit, which one is modified? Is it the current or is it the voltage? Voltage is modified or current is modified? Voltage is modified because we have broken the loop. We have mixed the voltage in series path, isn't it? We have mixed the voltage in series path. So this VI corresponds to the input voltage which is present in the input of the feed network, and VS is basically the input of the source. And these two are not the same. VS and VI, they are not the same. Right. But the current is the same because you have broken the loop and you have inserted something. So the current is the same. You have not connected anything in parallel. So the current cannot change. So IS is equal to II, but VS is not equal to VI. So what is the relation between VS and VI? If you simply apply KVL over there, VI is equal to VS minus VF. So negative feedback, VI is equal to VS minus VF. Accordingly, these polarities are given. VI is equal to VS minus VF. Right? So input resistance with feedback R in F is given by what? This voltage over there and this current over there. The ratio. VS, this voltage upon this current. So VS upon IS. What is VS?
1 plus AV.
What is VS? Now, how can you represent VS in terms of VI?
VI plus VF.
Huh? VI plus VF. Right? VI plus VF. And then what is VF? VF is equal to V times V naught. And what is V naught? AB times VI. Right? And accordingly, you find that VS is equal to 1 plus ABB times VI. Right? And this VI by RI is your good old RI. VI by II. That is your RI. So, R in F with feedback, this input resistance is equal to Ri multiplied with 1 plus AB into V. So, whenever you connect something in series, the easy way to remember this thing is that whenever you connect something in series, that means you are inserting more resistance. That is the case. If you connect something in series, previously you have something between these two terminals. Now you have broken the loop and you have inserted something new. So the new resistance will be more. Right? So whenever there is a kind of series mixing, that this input resistance will be increased. And whenever there is a shunt mixing, then the input resistance will drop down. Because if you connect something in parallel, this resistance will drop down. Clear? Okay. And here this D sensitivity factor is given by 1 plus ABB, as you know. And AB is what? AB is basically the voltage gain. And B is what? VF by V naught. So both of them, AB and B, both of them, they are unitless. And typically their product is AB is always unitless. A into B is always unitless. Right? Because the input to A is basically the output to B. Input to A is basically the output of B. And output of A is nothing but the input to B. Okay. So product of A and B is always equal to unitless. Always unitless product. So here what I find, AB is open loop voltage gain, which is unitless, and B the feedback factor, which is also unitless. In some other cases you will find that AB is having a unit of resistance and B is having the unit of conductance. Then also the product is unitless. But here we find both of them are unitless. And this particular architecture is known as voltage series. Voltage series, right? What is this called? What is this called?
Voltage current.
Current shunt. Now you take a look at here how this output signal is sampled. Series. We have broken the loop and we have just obtained the current like this, right? Shunt. So it's a current sampling and shunt mixing, or in other words, you can also call it current feedback. Current sampling and shunt mixing or current mixing. In our topology, we'll call it current shunt. Current sampling and shunt mixing, current shunt. So here you find over here, since it's a shunt mixing, so therefore this voltage Vs and this voltage Vi, they are same. Last time Vs and Vi they are not same. This time Vs and Vi they are same. Right? But the current is different. Is is not equal to II. Rather, Is is equal to II plus If. So some current will be taken care by this B. Some current will be taken away by this B. Okay? So this current Is, suppose it was 1 milliampere, and suppose 10% of it is taken by this B, and rest 90% is actually allowed to flow through the amplifier. Okay? So, what is the type of amplifier? Current amplifier. Because output is current, input is also current. Current amplifier. So, what is the unit of A? A is unitless. What is the unit of B? B is also unitless. Because here the current, the input is basically the I naught current, and the output is basically the IF current. Both of them are current. Right? Can you measure this input resistance? Input resistance? How to measure? What is the formula?
Vi by II.
Vs upon Is. Vs upon Is. What is the formula?
Is means II plus.
And Vs is equal to V. And accordingly, you just substitute Is in terms of II.
II plus IF হয়ে যাবে তাহলে এবার IF টা হয়ে যাবে আমার VI টোটাল রেজিস্ট্যান্স
Vs is equal to Vi.
তাহলে RI কমে যাবে রেজিস্ট্যান্স
Because you have connected something in parallel, so resistance will drop down. So the new resistance given by Ri upon 1 plus AIB. AIB. 1 plus AIB. Ri upon 1 plus AIB. Last time it was increased into 1 plus AIB because you have connected something in series. And this time you have connected something in parallel. So it will drop.
Output current direction টা ইন্টারনেট থেকে ছিড়ে দিয়ে গেলে
Now typically whenever we modeling two-port network, that is our convention that for a two-port network, this is positive, this is negative, this is positive, this is negative. That means this is the positive thing, and this direction of the current is considered to be the positive direction of the current.
Okay.
Conventionally, this is the description of any two-port network. For input port, the upper node is positive with respect to the lower node. Same is true for the output node. And whenever the current is entering when the current is entering this particular system, this current is considered the positive current. And whenever the current is leaving, this is considered the negative current. Okay. Okay. Now, this sensitivity factor, 1 plus AIB. A is unitless, B is also unitless. What is this one?
voltage
sampling. Voltage sampling. And you are mixing what?
voltage to current voltage to current
Mixing.
voltage
Voltage shunt. Voltage shunt, right? Voltage shunt. Because you are sampling the voltage and you are mixing what? You are mixing current. That's why you have the shunt connection there. Parallel connection. Okay. What about the feed network? This output is basically the voltage here, input is basically the current. So what is the type of the, what kind of amplifier it is? It's a
current amplifier.
It's not current amplifier.
Voltage to current.
Current is input, voltage is output.
Current.
So trans resistance amplifier you can call it. Trans resistance amplifier. Right. Because input is the current, output is the voltage.
V by I
Okay. Similarly for B, input is the voltage, output is the current.
I by V trans conductance.
So what is the unit of B? Conductance.
I by
The unit of A is of resistance and unit of B is of conductance. The product is once again unit. Okay, and voltage shunt, and finally this one. What is left? Current series.
এটা trans
Unit of A is of conductance, unit of B is of resistance. Okay, so we have discussed 4 such network. Yes. Voltage series, current series, voltage shunt, current shunt. But remember, all of this discussion is on a superficial level. Why? Because we don't know what is there inside this black box. Huh?
AGR beta.
No, not for this one. For other 3 cases also. Other 3 cases also. Voltage series, current series, voltage shunt, current shunt. We assume that okay, this black box represents an amplifier. Okay, this black box represents a feedback network, back network. But you don't know what is there inside. You have to explore what is there inside. Right? Okay, now let's start with a very simple amplifier circuit that you have encountered in this particular course. Okay, that part, as you know, this is basically summary of different types of feedback: voltage series, current shunt, voltage shunt, and current series. Right? If you have this voltage kind of sampling, if you have voltage sampling, then the output resistance will drop. If you have voltage there, output will drop, output resistance will drop. And if you have current there, this will increase. Similarly, whenever you are connecting something in series, that means it's a voltage. Voltage mixing. If you connect something in series, that means input resistance will increase. Something in series, input resistance will increase. If you connect something in shunt, this input resistance will drop. Clear? Okay? That's the summary basically. Okay. Now let's move to this circuit. Let's move to this circuit. You have already encountered this circuit. This one? What is that? What is that biasing arrangement called? Huh? And we have fixed bias over there, and apart from that, you have an emitter resistor connector. Right? If we don't have any RE over there, what was the gain expression? Minus GMRC. Now, if you have this RE over there, what was the resistance? What was the gain? Minus RC. That you already know. But that time, you don't have an idea whether it involves any feedback or not. I have told you, I have explained during our discussion in the yes, but you don't know where is this, where is the feedback element present, right? At that point of time, obviously during our discussion in the BJT biasing, hopefully you can remember in the BJT biasing chapter, I have incorporated where this this feedback action is basically taking place. Okay. Now let's observe, let's visualize this circuit from the context of a feedback amplifier. You know how to draw the small signal model? Those who are new, for them, once again I am telling it. This BJT is modeled by means of 3 element pi model. One is this R, which is there between base and emitter, then you have this GM V pi between the collector and the emitter, and then you have this R naught between the collector and the emitter. Right? And previously what we have done, we have connected these two together. This is the emitter terminal. Now we have, and then you have this RE. Right? Because the RE is there between the emitter to ground. Emitter is not grounded, it is grounded through RE. Okay? And then you have how to place RB. How to place RB? RB is from base to AC ground. Which is the AC ground? Base to AC ground RB. How to place RC? RC is from collector to AC ground. So collector to AC ground. This is AC ground. Right? Clear? How to place this BS between the base and the AC ground. Done? Now tell me, is it a feedback network? Is it a feedback amplifier? Hopefully yes. Hopefully yes. Then you have already studied 4 such models: feedback, feed model, and the feed network and back network. Then you have to fit this particular small signal model in any one of these 4. Any one of these 4. Now you tell me whether it's a current sampling or voltage. First you tell me whether it's a current sampling or voltage sampling. Current sampling or voltage sampling. To identify where is the feed network, where is the back network. Where is the feed network and where is the back network. You have to identify. Current sampling or voltage sampling. You have these 2 lines. No, you have these 2 lines for getting the voltage. Have you broken this line?
Current sampling.
You have broken the line. Right? You have broken the output side of the feed network.
Output side. What is output?
Huh?
What is voltage?
Voltage sampling.
And a current.
How to identify whether it's a voltage sampling or current sampling? Whether the output side, whether the loop is broken or not. If the loop is broken, that means current sampling. If the loop is not broken, if you consider that loop is not broken, in that case it will be voltage. That means you have connected something in parallel. Now, have you connected something in parallel? Hopefully this is your back network. Hopefully this is the back network. This is the input of the back network, this side. Right? How have you connected? Have you broken the loop? Yes. You have broken the loop. Right. What about the input side?
Input side
have you broken the loop?
No.
Huh? Yes or no?
No.
These are the 2, no? These are the 2 nodes. How have you connected? They are broken, na? Right? So once again, let me move to this one.
Current
Current to voltage.
This one. Does it look similar? Yes or no? This loop is broken. This loop is also broken. Right? Current series. Current series. Both the loops are broken. Current sampling and not current mixing. Series mixing means what? Voltage mixing. Voltage mixing. No, forget about GMRs. It has no connection with GMRs. Okay.
তারপরে এই ছবিটা একবার একটু ঘুরে এখানে লুক
Let me mark. Okay. This is one network. Other network. Upper one is the feed, lower one is the back. These are the two terminals. These are the two terminals for the back network, for the feed network, and these are the two terminals for the back network. Output terminals for feed, input terminals for the back. How are they connected? Parallel connection? No. You have broken the loop and you have connected. Series connection, that means current sampling. How have you mixed the output of the back network to the input of the feed network? Once again in series. Voltage. That means you are feeding the voltage. Right? Okay? So current series. What is the expression for the voltage gain? What is the expression? What is the expression? So you see here, what is the relation between VA, Vpi, Vs and Vf? Vpi is equal to Vs minus Vf. Negative feedback?
Vs minus V.
Vpi is equal to Vs minus Vf, right? And what is VO? VO is nothing but this current IO times RC almost, because you have some resistance R naught over there, but you can neglect. Almost equal to I naught RC, right? I naught RC. What is VF? What is VF? This voltage. This is nothing but times RE, right? Okay. You got I naught is equal to Gm times Vpi, because there you have R naught, some kind will be there through this. If you just plug in these values, Vs is equal to Vpi plus Vf. Vs is equal to Vpi plus Vf, because Vpi is equal to Vs minus Vf. So what is Vpi? Vpi is equal to I naught by Gm, and Vf is equal to I naught times Re. So therefore we get Vs is equal to I naught into 1 plus Gm Re by Gm. Any doubt? No, Gm Vpi, if you just consider this one, this output current is I naught, right? Now here you have Gm Vpi, and obviously some kind will be there through R naught. Now we are not just neglecting that part. So that's why Gm Vpi is almost equal to I naught. Some kind will be there also. Okay. So Vs is equal to I naught into 1 plus Gm Re by Gm. Okay. What is AGF then? Because it's a current series amplifier, current series feedback network. That means your output is a current, input is a voltage. So voltage to current conversion. So the type of amplifier is a transconductance amplifier. So that's why I have written like AGF. G stands for conductance. What is that? I naught by Vs. I naught is your output current, Vs is your input voltage. I naught by Vs. What is I naught by Vs? This one simply. I naught by Vs is what? Gm by 1 plus Gm Re. What is from AGF? Can you calculate AVF? Yes. If I allow this current, output current to flow through a resistor, then it will give you the output voltage. What is that? Simply I naught times RC. Isn't it? Then ultimately it reduces to GMRC by 1 plus GMRE with a minus n outside. Minus GMRC by 1 plus GMRE. Right? Now if GMRC, if GMRE is much bigger than unity, this is obviously equal to minus RC by n, which you have already noticed. You know now, for this kind of amplifier, what is the gain? Minus RC by R. But remember, this minus RC by RE is having this particular form, minus GMRC 1 plus GMRE, and then you can recognize this as, you have recognized this as A by 1 plus AP in that particular form. Clear? Any doubt? So this is a current series feedback amplifier. Okay? This amplifier, hopefully you have noticed. You have noticed now this kind of biasing arrangement you have noticed. What is that called? Collector feedback bias. Right. There's a DC biasing out there, but apart from the DC biasing, there's also a small signal feedback is present. Now, if I just draw the small signal model, is the small signal model okay? Or do you have any doubt? Try to understand. Between base to emitter, between base you have V pi, between collector to emitter you have GM V pi, between collector to emitter you have R naught, right? From collector to ground you have RC, okay? And what else? You have RF connected between base to collector. So this is your base region, base terminal, this is your collector terminal. So I can connect like this. Okay? And this VS is connected like this. Have you broken the loop? No. It's not current shunt.
Voltage to shunt.
It's not current shunt. You have sampled the voltage, right? You have sampled the voltage. You have sampled the voltage. You have sampled the voltage, and how did you mix it? Shunt means what? You are mixing current mixing, right? So voltage current or voltage shunt? You can call voltage shunt or voltage current. Voltage current or voltage shunt. Okay. Okay, fine. So voltage shunt feedback. Any doubt? No doubt. Since it's a current mixing, so this current II and this signal current IS, these two are not the same. Right. So IS is equal to II plus IF. And what is V pi? V pi is the current which is flowing through this R pi multiplied with this resistance R pi. That is II times R pi. That is V pi. Okay. What is V naught? V naught is nothing but minus GM V pi times R naught parallel RC, because this is the current and R naught parallel RC is present over there. R naught parallel RC is over there. So V naught is equal to minus GM V pi times R naught parallel RC, or almost close to RC anyway. Or you can write it like minus GM V pi RC. Okay. What is the relation between V naught and IF? IF is equal to, what is the relation between V naught and RF? Yes, look at the direction of this IF. Look at the direction. Look at the direction. This one is V naught. This one is V naught.
V naught is equal to minus IR.
This is V naught. And the current is flowing in that direction. That's why V naught is equal to minus IF. Okay. Okay, so you know that IS is equal to II plus IF. So what is II? I can write, instead of II, I can write V pi upon R pi. That was the value for II. And for IF, what I can write? Minus V naught by RF. Okay. So then, V pi is equal to V naught minus V naught by GM RC. From here, V pi is equal to minus V naught by GM RC. So if you just plug in these values, minus V naught by GM RC, and you have R pi outside, and minus V naught by RF. So if you take minus V naught outside, so 1 by GM R pi, that is beta. So 1 by beta RC plus 1 by RF. What kind of amplifier it is? It is giving you voltage in response to current. It's a trans resistance amplifier. You have to find out this ARF. VO upon IS. Right, VO upon IS. What is that? Already have calculated IS is equal to minus VO into this one. So VO upon IS is given by how much? This minus 1 by 1 plus beta RC plus 1 by RF. That is given by this one. So ARF is given by minus beta RC by 1 plus beta RC by RF. Trans resistance gain you have already calculated. ARF. So what is AR there? What is AR? AR. What is AR?
ARF is equals to.
That means you can always write AR. What is the trans resistance gain without any feedback. What is that? This is simply for this particular amplifier. If I consider trans resistance, what is the voltage by current? Voltage by current. So what is the voltage? Output voltage. That means GM V pi times RC. GM V pi times RC. That is the output voltage, right? And what is the input here? That is simply what is the current? What is that current called? So this AR is how much? Let me change the color here. Make it green or make it blue. AR is how much? AR is basically VO by IS without feedback. Right? That means this IS is also equal to II. Okay? What is VO? What is VO? There is a minus sign. Okay, I can call it mod only. Okay, the mod. GM V pi. Then you have RC upon II. What is that II? V pi by R pi. Right? So V pi gets cancelled. GM R pi RC. GM R pi RC. What is GM R pi? Beta. Beta RC. Basically, you have a minus sign there. Basically, a minus sign. Right? So beta RC is your trans resistance gain without feedback. Trans resistance gain without feedback. That is beta RC. Okay. Now you take a look at this expression. What is ARF? ARF is equal to beta RC by 1 plus beta RC by RF. So that particular form, no? You can write this as
A by 1 plus A.
Can you write in that particular fashion? AR upon 1 plus AR times B. What is AR? AR is equal to minus beta RC. What is B? B is equal to minus 1 upon RF. Minus 1 upon RF. What is the unit of AR? Resistance. What is the unit of beta? Or what is the unit of B? That is conductance. So AR, basically AR is equal to minus beta times RC, and B feedback factor is given by minus IF by V naught, that is equal to minus 1 by RF. Right? What we have got over there, ARF, that is equal to minus beta RC by 1 plus beta RC by RF. That means AR by 1 plus AR times B. Okay? So it's a voltage shunt feedback amplifier. Clear? Voltage shunt. All of them, both of them, current series and voltage shunt, can be constructed using common emitter single stage amplifier. Single stage common emitter amplifier. Right. The last one was a common emitter amplifier with emitter resistor. This one is a common emitter amplifier with a feedback resistor between the base and the collector, between the input and the output. Now, still we have two other types of feedback network. What are those? Voltage series and current series. But unfortunately or fortunately, this voltage series and the current shunt, these two feedback amplifiers cannot be constructed using a single stage common emitter amplifier. Unfortunately or fortunately. Now, obviously, there are two aspects. There are two aspects. First of all, let me tell you the unfortunate part first. The unfortunate part is that this voltage shunt and current series, you have already observed that voltage shunt and current series, they can be constructed using single stage common emitter amplifier. Voltage shunt and current series, single stage common emitter amplifier. But voltage series and current shunt, they cannot be constructed using a single stage common emitter amplifier. So I have told you that unfortunately or fortunately. Why unfortunately? Because they cannot be constructed using single stage common emitter amplifier, but multi-stage or two-stage common emitter amplifier. That's it, unfortunate. And why fortunate?
Common emitter aspect.
The fortunate is no, that's not the big deal. The thing is that they can be constructed, voltage series and current shunt, they can be constructed using single stage but non-common emitter amplifier. Single stage but non-common emitter amplifier. Non-common emitter. Single stage but non-common emitter. Either common base or common collector. Now tell me, suppose I would like to have, I will not discuss this voltage series and current shunt today itself. But just you tell me, suppose I would like to have say a voltage series amplifier, right? Voltage series, right? So I have already told you that it is not possible to design this voltage series amplifier using a single stage common emitter amplifier. Multi-stage it is possible, two-stage it is possible. So you have to have some amplifier, single stage amplifier, either base or common collector, which can yield this voltage series. Now tell me which one is applicable. Whether you go for a voltage series or whether you go for a common base. How to understand? So which one to pick up?
Small signal.
No, not for no, you don't require this small signal. I have to construct a voltage feedback amplifier voltage series. So I can do that. So next day I will show you that voltage series can be constructed using a single stage non-common emitter or multi-stage common emitter. But whenever you are going to design this voltage series using a single stage amplifier, then which one to select? Is it a common base or common current?
Common current.
Why? Why common base or why common current? Obviously not both. Either common base or common current. Huh? A reason? No. Not using the structure. But you can answer this question. You can answer this question if you just follow the input and output resistance. For voltage series. For voltage series.
Output range.
No, for voltage series.
Output resistance.
Which resistance is larger? Input or output?
Input.
Input is larger. For voltage series, input is larger. Series connection and voltage sampling, that is shunt sampling. So output resistance is small. So for voltage series, we have to search for an amplifier for which R in is large and R out is small.
Common collector.
That's the common collector. So this voltage series can be constructed using a single stage common collector. Right? On the other hand, if you go for a current shunt amplifier, just the reverse. For current shunt, you are mixing in shunt. That means resistance will drop. And current shunt, that means current sampling. So you have broken the loop and you have taken this connection, right? So input resistance will be less, output resistance will be more. What kind of amplifier it is? It's a common amplifier. So voltage series can be constructed using common collector, single stage common collector amplifier, and current shunt can be constructed using single stage common base amplifier. Apart from that, both of them can be constructed, which is an unfortunate part. Both of them can be constructed using multi-stage or two-stage common emitter amplifier. Two-stage common emitter amplifier. Means if you have this two-stage common emitter amplifier, in that case, the corresponding small signal model will be even more complicated. Right? We will discuss this one in detail in the next class.